Let's take a look at problems that were given to the class today. So, so here we have a force and magnitude of force is given, right? And so when you look at this problem here, the free body diagram is you do have weight, you do have a normal force, and you have this force which is given, right, going like this much, and this is 250 Newton. Okay. So what we need to do, coefficient of kinetic friction is given. So we have coefficient of kinetic friction given. We have this force also given. The mass is also given. And the distance the block moves in a rough surface is 50 meters. So what is the work done by the applied force? So applied force is this one. So the work done by this external force is F, the cosine of the angle between the force and the displacement of the block. So the block displaces like this, right? So the angle between the force and displacement is this angle here. And I think this is given. Yeah, it's right there, 30 degrees. Yeah, 30 degrees. So the work should be 250 times 50 times cosine of 30. This is the work done by the force. Now, the work done by gravity is zero because, see, the work implies cosine of an angle between the force and the displacement vector, and the angle of gravity as well as the angle of normal force is 90 degrees. So the work of these two forces is zero. Cosine of 90 is zero. Now, friction is a force that is given by the coefficient of kinetic friction in this case, because there is motion, times the normal force, correct? And the coefficient of kinetic friction is given, is 0.1, right? Now it remains to find what is the normal force. This is a tricky one, because you can come and say, well, normal force is mg, but it's not. Why is not? Well, because in addition to mg, look at this external force. This external force also gives a projection in the y direction, which is equal to its value cosine of the angle between the force and that axis, which is 60 degrees, or is the same thing as sine of 30, right? So the projection of f in x is f cosine of 30, right? And the projection of f along the y direction is f sine of 30. And that is going to be equal to your normal force. So therefore, the work of friction, writing right here, is the negative. Remember, friction is a force that is external, and I forgot to include it in our free body diagram, is a negative of F times the distance covered, so the negative of this big coefficient, 0.1, times this big expression times d, okay? Let's see what else here. We did that in class, correct? Let's see this one. We have a 69 kilograms baseball player that slides. He starts his slides at the speed of 30.9 meters per second. And his speed is zero just as he's reached the base. So imagine he starts sliding here and he stops at the base here. So he has an initial velocity of 3.9 meters per second and it stops at 0 meters per second, okay? And here's the much he covers. And the coefficient is given. Kinetic because he's moving, is zero point 0.6. Determine the mechanical energy lost during friction. So when you think about energy, we always think about 2 points. Remember, we forced this concept in class. You have two situations, A and B, like when you leave your house, you have $100 money in your wallet, and then you leave your house, and then you come back later, you have $56 in your wallet. So you should be able to account for $44. Where did you use it? Where did you spend it? And then that's how we do with conservations of energy. We have two positions or two situations, two different configurations, A and B. A is when the player starts sliding, B is when he stops at the base. And then you go down the energies that you have at that moment, right? And then how about kinetic energy? Does it have kinetic energy at point A? Oh, certainly it does. Half m times speed squared, but at point B, the person stops. How about gravitational potential energy? Yes, it does. But as the same ground level, because see, it's all in the ground level. So there is no raising of the player or going down in a pit or something. There are no springs in this problem. So pretty much that's it. Well, but I have work done by other forces. So what are the other forces in the system besides gravity and normal? Remember, gravity and normal, as we saw in the previous problems, don't do work on the system because they happen to be perpendicular to it. But friction does, and the work done by friction is the negative of force of friction times the distance, right? And this negative is because the cosine of an angle, and the angle is 180. So pretty much that's it. You add these two quantities, and the total energy should be conserved or should be accounted for. So when you add those, oh, I'm sorry, this is not correct. It's not zero. It's not zero. There you go. So when you add these two terms, so you got half m v squared minus F friction times D is equal 0, right? Is equal to this part, which is 0. And then you can then calculate the mechanical energy loss. This is the mechanical energy loss. So you had initially a certain amount of kinetic energy, and it was lost by the friction, and this is given by that. And the distance d is equal to half mv squared divided by the coefficient of friction. So when you solve this side of the equation, you can then resolve for t. How about this? What is this? A warehouse worker is pushing a 90 kilograms crate, horizontal force, speed is given. He encounters a rough horizontal section of the floor, 75 long, coefficient of kinetic friction is given. Determine the magnitude and direction of the net force acting on the crate while it is pushed over a rough surface on the floor. So let's do the free body diagram. So you have a crate over there. That's the mass of the crate, the horizontal force that is being exerted on the crate by the worker, 287 newtons, and there is a speed 0.88 meters per second. Okay, supposed to be a constant. He's going with that speed, right? And then he encounters a rough horizontal section on the floor that is this much long and where the coefficient of kinetic friction is given. Okay, so pretend now that he is encountering this rough surface and pretend that the block is just a point. So when he meets that, Here is the friction force that resists the motion. So when you do your free body diagrams, because it's asking what's the magnitude and direction of the net force, what is the net force? The net force is the sum of forces in X. So you have a 287 newtons to the right, and you have a friction to the left, okay? This is the net force. So to find the net force, you must find out what is your friction force. And the friction force is equal coefficient of kinetic friction times the normal force. Coefficient of kinetic friction is already given. What is it? 359. And the normal force is, in this case, mg. mg. Right? So we have that. We plug this number in here. And then we can get the net force, which is the first result. The term the net work. Well, the net work would be equal to the net force, which we just calculated, times the displacement, right? So you take the value, which is, if they did it right, is this number times 0.75, okay? And they should get it right. Find the speed of the crater. So how can we find the speed of the crater when it reached the end of the rough surface? Well, we can use what we learned in the lab today is the work, total work of all forces. Remember, you also have, in this case, gravity to be completed with the free body diagram. We have gravity and normal force, but those two forces, gravity and normal, they do not do any work on the system because they are perpendicular to the system, right? Cosine of 90 is 0. Therefore, the total work is equal to the change in kinetic energy. That was the subject of this week's lab. So the total work, if they did correctly, is this number, calculated in the previous section, is equal to the change in kinetic energy, which is half mass is given, right? We have the mass, final velocity square minus initial velocity square. Put a parenthesis there or you're going to get it wrong. Well, the initial velocity is known. We know the initial velocity. 0.88 is right there, right? This is 0.88. And then we can find the final velocity since the mass is given and we have this number here, okay? What else? What is this? You have a toy plane, the mass is given. The mass is given, it's tight twist. Remember, you have, consider that you have a circle, you have something change in direction like a curve, and you have motion. You are going to deal with centripetal force or an acceleration. Centripetal acceleration is v squared over r, and centripetal force is mv squared over r. Now, centripetal force is not an additional force to the system, but is the net force along the direction towards the center of rotation that allows your system, in this case the little airplane, to rotate, to go in a curve. Okay. This is very important. So when you solve this type of problem, the first thing you ought to do is to come up with a decent free body diagram. So let's read the problem. We have a toy plane, the mass is given, it's tied to a string. So if there is a string, there is what? Tension. Very good, there is tension. It's made to travel at a certain speed. So I have a speed, 23 meters per second. The radius is given. So this distance here, not 1.7, but 17 meters. The person holding the string pulls the plane in increasing the tension in the string, increasing the speed of the plane and decrease the radius of the plane's orbit. What is the net work done on the planet if the tension in the spring increases by a factor of 4 and the radius decreases by 8 meters? So the initial radius minus the final radius is pretty much 8 meters. So we have an original radius of 8 meters and original radius, I don't know the value. Oh no, I know the value, 17. And then the final, so 17 minus final radius is 8. And then, so the final radius is 9 meters, right? So it starts with 17 meters, and then it pulls the little toy, and the toy's airplane, as it pulls in, it increases its speed and the radius diminish. And what is the net force done on the plane if the tension spring increases by a factor of 4? So the tension initial is T naught, and the final tension is 4 times as big as the initial tension. So what is the net work done on the plane? Well, the net work, the total work, which is the net, I mean, the idea of a net is the total, according to the work kinetic energy theorem, is equal to the change in kinetic energy. So the only thing, believe in me, you need to do to solve this problem is to find the final kinetic energy minus the initial kinetic energy. And then the problem is solved. So basically, you need to find the final velocity, the initial velocity, since the mass is given. But the centripetal acceleration is given by the speed square over r. So you know the initial speed is 23 meters per second. Okay, and then you can use what do we need to find, by the way? Oh, what is the network? We want to find the network. Oh yeah, so the final position, the tension increased, so we can use the initial tension. The initial tension is the centripetal force, is m t naught is m v squared over r, right? R in the initial phase is pretty much 17 meters. The initial velocity is given, so you know the value of the initial tension. So the final tension was increased by a factor of 4. So you can use that fact to determine the velocity after the airplane is pulled in, because the final tension is going to be mass times v final square divided by r, right? And you have a ratio between the final tension and initial tension. So we can find the velocity final. And once you find the velocity final, plug it in here, you have the initial velocity, and you have change in kinetic energy. We have the net work done in that process. It's kind of a tricky problem. We did this one in class. What is this? As shown in the figure, we have a 1.5 kilograms box that is held at rest against a spring. So we have a spring there. See that the spring is compressed, and D is is how much the spring is being compressed. So at this configuration, if you call that A, the spring has a potential energy of half k d squared, right? Okay. Spring constant is given. K is 700 newtons per meter. Compressed to a distance d. Okay, we got it. When the box is released, it slides across a surface that is frictionless. So this is pretty much frictionless, except for a rough patch. So we have a little patch that has a coefficient of kinetic friction given. So coefficient of kinetic friction is 0.4. And the length of it is 60 centimeters. And I'm converting that to meters. I can check now, Sophia. I'm taping.
I know, but I checked the back of the book and they had the answers and I got everything right.
if the length of the box is 1.7 meters, if the speed of the box is 1.7 meters per second, after sliding across the rough, so when you get to this point, the speed is 1.7 meters per second, determine the initial compression of the spring. So here's your point A. Here's your point. Yes, point B. Then what do? Do a little table. A, B. How much money you have in the morning? What's the energy budget you have in the very beginning? Well, go down your list. Kinetic energy, point A, 0. Right? It's not moving. The block is not moving. It's stationary. But at point B, you do have a kinetic energy given by half mv squared. You have m. You know what half is 0.5. V squared is what you want to solve for. No, you don't want to solve for. V is given, is 1.7 meters per second. What do you want to solve for? Oh, you want to solve for the initial compression of the spring. Okay, got it. Now, what else do we get? Do we get gravitational potential energy? No, everything is in a slope. It doesn't change. Do we have springs? Gravitational potential energy in the spring. Oh, yes. At point A, I have half k times d squared. Half k d squared. K is given, is the spring force, 700 or constant, 700 newtons per meter, and d is how much the spring is being compressed. But at point B, once the block reaches this part of the exercise, the spring should be entirely relaxed, right? So the spring is free. So you don't have energy in the spring. The spring is relaxed. Now, how about any other force? Don't forget this. So we have a work done by other force. And this other force doing work now is the friction force. So the work done by friction is negative value of the friction, which is coefficient of friction times normal force, in this case mg, times how much of that patch that was subject to friction, 60 centimeters. And this is the work done from point A to point B. And then you got there. See that? How simple that is? So what do you do next? You add these three quantities and make it equal to these three quantities. So let's write it right here. So half of k d squared, and we want to solve for d. K is known. In fact, minus coefficient of kinetic friction mg times 0.06 is equal to half mv squared. And then you can solve for d after you play a little bit with mathematics. Okay. And I guess this looks like the Fat Colorado exercise. So let me know if you can't do the others. The others should be okay to do. All right.